So before the break, we were looking at these omega limit sets and addressing why they are important, right, in the global dynamics of the delay equation that we are studying. And the key in the case of this delay equation, nonlinear delay equation 2, is that actually we will be able to characterize the omega limit sets in a very precise way. So what are the candidates to omega limit sets? And anything else, any other initial condition that doesn't lie in an omega limit set will eventually arrive at 1. This is what the definition of omega limit set is telling us in the first place. So the reason why these omega limit sets are important is that if you let your system run for a while, anything you observe, say that you have a numerical simulation, anything you observe will eventually be sitting in an omega limit set. So yes, this property A1 star will turns out to allow us to describe these omega limit sets very precisely. Rather than doing it than giving you the theorem in general first, I will give you first an intuition of why this is the case. So let us look at the following projection. Definition. Well, I don't think it has a proper name, but we can call it planar projection. There are people who call it pseudo phase plane projection. There are very strange names for this same object, which is used widely in the study of delay equations. Okay, but the planar projection to us is the map P taking a continuous function, from the interval to a real line, and giving us back a point in R2. And what we do is very simple. We feed in a function in history space. Maybe, what did I do? Yes, we feed in a function phi, and we get back the evaluation at 0 and the evaluation at -1. So we are taking in one whole function, huge phase space, and we are getting back a point in R2. Naturally, this is a rather steep decay in dimensions. We went from a very, 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 very large vector space to a very small vector space, right? And we expect that this projection is losing a lot of information, because how could these points in R2 retain any of the properties of the original dynamical system living in infinite dimensions, right? So we have solution curves, which are curves of functions. And now we are only looking at points in R2 derived from these curves of functions. So the question is, can we expect the P to preserve any dynamical information from 2? Well, let us look at special solutions first. Let's say that I start with an equilibrium of my nonlinearity, my delay equation 2. What does the projection give me back, right? What's an equilibrium is what? A single point, right? It's just a point. So consider an equilibrium, x0 in Z. From now on, I will call this Z. That is a point such that applying the semi-flow leaves it stationary. Well, clearly the orbit of the equilibrium is the point itself, a single point in Z. And what I get after applying P is also a point in R2. Okay, so in principle, this is a faithful description of my equilibrium. How about a periodic solution, though? So x0 in C periodic with period P. Well, you see, now the orbit has more points, right? Now the orbit is T x0 with T in R. And I'm comparing this to the xt minus 1s with T in R. And will these two sets be somehow analogous? Will they be homeomorphic? Will they not be homeomorphic? Do I lose any information when projecting a periodic orbit is my question. And what's surprising is that you don't lose any information. And the reason you don't lose any information is thanks to the zero number. So, surprise, both sets are homeomorphic. And this deserves a lemma, actually.
Only for periodic orbit or for the global dynamic?
Oops. This homeomorphism is in general true for any omega limit set. So if you have a set that you know is the omega limit set of a trajectory of this equation, then it will be homeomorphic to the projection, to its own projection. But the proof in general requires many details, but it's very easy to prove for periodic solutions. And actually, in the remainder, I will only use the proof for periodic solutions. So yes, maybe let me remove this. Let's write a lemma. So let x of t be a periodic solution of 2 with period p bigger than 0, and denote gamma, the x sub t, that is tt x zeros, with t in R. Yes. Then the map, and I didn't really give it a name in the script, but it's a map from the circle to p of gamma. So that's the projection of gamma by this planar projection. That's the points xt minus 1 is a ck embedding. Oops. So I never gave the map, sorry. So t gets mapped to px sub t is a ck embedding. So what's this telling me? This is telling me that if I draw here x of t in the x-axis and xt minus 1 in the y-axis, and I draw the projection of the orbit gamma, then the projection cannot look like this, for example. Right? Because this is a figure 8, and here you have a point of self-intersection, and then this map is not injective, for example. So what this is telling me, this was a very bad idea, what this is telling me is that when I project the periodic solution, then it has to look like a Jordan curve. Can it have kinks though? Well, no, because if it had kinks, then it wouldn't be a C1 embedding. So even more, it tells me that the projection is a ZK Jordan curve. So it's very nice. All of the information about the periodic orbit is then encoded in this two-dimensional drawing. And how do we prove this? There is a second part to this lemma that I will go into a bit later. No, I should go into it right now, actually, which is that, moreover, if gamma 1 and gamma 2 are two different periodic orbits of 2, then the projection of gamma 1 doesn't intersect the projection of gamma 2. So maybe this is gamma 1, p gamma 1, sorry. Then p gamma 2 is again a C1 Jordan curve, and maybe one is inside the other, but it could also happen that they are just apart. Neither of them is inside the other. Okay? So either of these two situations is possible, but what's definitely not allowed is an intersection. Something like this is not possible. This will be a property that we will exploit thoroughly later when we try to describe the set of periodic solutions of a special example. Okay?
You allow me to say something?
You want to comment something? Yeah, sure.
同学，在无穷的空间中，一个 periodic solution 一维，它现在证明了，你把它投到二维，你只看这个 xt 跟 xt minus 1这个 delay coordinates， 它也是一个 curve。所以这个一维的 curve 在无穷的空间中被 project 到这平面上的这个一维的曲线，这整个过程是一个 homeomorphism 或 diffeomorphism。所以这整个过程中，你整个几何结构没有改变，而且呢，你看那个 periodic orbit 这样不能够相交嘛，代表什么意思？代表你有个 order， 你可以排序。又来，你看，你要想一下、这种事情你要证明是极度难的东西。如果今天是无穷维，你在二维的敞开 bandation 可能有这样的，但是三维、四维、五维 ODE 你甚至都不能做其他的测试。那为什么一切可以？会就是有那个 zero number。你想想看，什么时候会相交？相交的时候代表，所以你的 zero number 会 drop。可是我们刚刚说 periodic 的时候，觉得 zero number 不会。但是整个证明就是用到 zero number。Okay. So I already tell the man a sense of your proof. Yeah.
Yes. So now we will quickly prove this, and it's an easy, well, it's not an easy consequence, but it's easy once you know how to do it. So how do we do this? Is it fine if I erase this? We shall prove first that indeed projecting this gamma onto two dimensions gives us a homeomorphism. So on the one hand, look, on the one hand, the continuity of the projection is clear, right? Because we started with a continuous function from the very beginning. Yes, because we have a continuous function. On the other hand, in practice, the only thing that we have to check is the injectivity of this projection from gamma to R2. And that's what we will do. Yes. So proof first of this embedding, we check that P is injective on gamma. That is P of xt, they call this, yes, P of xt equal P of xt plus tau implies that tau is a multiple of the period. So we proceed by contradiction. So by contradiction, suppose P of xt equals, yes, suppose that P of x0, I want to match it with the notes, equals P of x sub tau for some tau. Notice that if the projections are the same, this tells me something about the derivative of about x dot of 0 and x dot of tau, right? Because what 2 is doing is evaluating the function x of t. So g is essentially evaluating x sub t. Sorry, a fancy way of writing this is to write p of x sub t, right? So if those two projections coincide, then so do the derivatives. So now I can define new functions, new solutions. x1t equals x of t, and this is just formality. And x2 of t equals xt plus tau. And both of them solve 2. Why? Because 2 is an autonomous equation. It doesn't depend on time. So if I shift any solution by some time, this will still solve the differential equation, right? So now we look at y of t, the difference of solutions, x1t minus x2t. And can anyone tell me what's happening at 0 for y of t? What does y of t look like at 0? What's y of 0? So y of 0 is?
Longer.
Yes?
0, I think, right?
Yes, y of 0 is 0.
Yeah.
Y dot of 0 is? Remember this fancy way of writing the differential equation? So y dot is 0, because x dot 0 equals x dot tau, and now we are subtracting one from the other, right? So this is again 0. Now, on the one hand, y is a difference of solutions, right? And we already commented at the very beginning of the other part of the lecture that the difference of solutions of 2 solves 1. So we can talk about the 0 number of y, right? On the other hand, there is this theorem 171 part 4, yes, that tells me that if the 0 number is constant, then all of the zeros are simple. But we just constructed a function that solves this guy, that solves 1, so it has a 0 number, but the number of zeros is clearly, the zeros are clearly not simple because I have a double 0 0. So the 0 number is not constant. So that means that, this means that there is a double 0 of y. And then by theorem 171 4, I believe,
Yes.
0 number is not constant. Vy dot t is not constant. So that means that we can find a time t1 smaller than a time t2 such that the 0 number of y dot t1 is strictly smaller than the 0 number of y t2. Larger. Why larger? Precisely. The 0 number is a non-increasing function. So if it switches values, they must decay, right? So maybe 10 years ago, y of t used to have 5 zeros, and after 20 years, it dropped 2. And the 0 number used to be 5, and now it's 3. Okay, but remember that this guy, yes, y of t is actually a periodic function, right? Do we agree to this? Because it's just a difference of 2 solutions along the orbit, along the periodic orbit. Both of them have period 2, so when it's up to p, so whenever I subtract them, I still have period p. Okay, so this means that I can always find, how did I do this? Here I wrote quasi-periodic. I don't know what I was thinking. It's periodic. Okay, so that means that y of t1 plus np is y of t1. What if t1 plus np was actually larger than t2 though? Which I can always do by choosing a huge n, right? Well, then this is telling me that v of y dot t1 plus np needs to be smaller or equal than v of y dot T2, right? And here I'm using the monotonicity, the fact that V is an increasing function. Maybe I should have written them the other way around. Yes, sorry. This is clear. Then I have what? T1 is smaller than T2 is smaller than T1 plus NP. And on the other hand, I have V of Y dot T2 is larger equal V Y dot T1 plus NP. And this is from the same theorem on the zero number, but this is part 3, if I'm not wrong. But remember, periodicity. This is again equal to V of Y T1. But hold on, we started with a dropping. So we actually have that this is strictly larger than V of Y dot T2. Somehow V of Y dot T2 is larger than V of Y T2. How is this possible? There is only one way in which this contradiction can be solved. And that's that we started with a wrong premise. So yes, it means that x0 had to be equal to x tau, right? And because we are on a periodic orbit, this only happens if tau is a multiple of the period. So we reach a contradiction here. How do you write write contradiction in Taiwan? Like this? This is fine. Okay. So contradiction. So we must have started wrong from the very beginning. And yeah, essentially, the only way in which this is solved is if tau is NP. And then what happens is that Y is identically 0, and we cannot define the zero number in the first place. So from this, we obtain that P has to be an injective function. P has to project gamma injectively onto P of gamma.